Hello, my name is Brent Eldridge, and this is Chemistry 150, Introduction to Organic and Biological Chemistry. We are going to focus mainly on organic chemistry this semester and learn the fundamentals of molecular formulas, structural formulas, condensed formulas, and line formulas for basic organic compounds that can be classified as aliphatic, which are alkanes, alkenes, and alkynes, and aromatic compounds such as benzene. We'll also learn about some of the basic chemical reactions with hydrocarbons or organic molecules, and we will start in Chapter 10. We are using Deniston's 8th edition book, and the beginning of the chapter, first of all, what is organic chemistry and why is it so special? Many of the compounds we deal with on a day-to-day basis are organic in nature. That means they're carbon-based. So what does that mean? Why is carbon such an important element in chemistry? Well, when we look at the Lewis dot structure for carbon, or let's step back and let's look at the electron configuration for carbon. It's 1s2, 2s2, 2p2. So carbon has 6 protons and 6 electrons, and those 6 electrons, if we use a dot here to represent the nucleus, 2 electrons are in the first shell, called the inner shell, and then we have 4 electrons in the outer shell. So in chemical bonding, it is the outer shell electrons excuse me, that are involved in chemical bonding. So a Lewis structure represents these valence electrons or outer shell electrons as dots. So you'll see that I have 4 dots around the carbon. So carbon's special because it has the ability to bond with 4 other electrons and create multiple bonds. So we can have something like methane, which is carbon bonded with hydrogen. So here's carbon with its 4 valence electrons, and a hydrogen can bond here and here, here, and here. So that would be carbon with 4 single bonds. If we look at something like carbon dioxide, we have carbon, again 4 valence electrons, and we have oxygen, which has 6 valence electrons. And again, the driving force here is for electrons to have a full outer shell of 8, and carbon and oxygen does this by sharing their electrons. So there'll be a shared pair between the oxygen and the carbon. Same thing here, same thing over here, and same thing here. So when we clean this up, we will get carbon with the double bond to each oxygen, and then each oxygen will have 2 non-bonding pairs or lone pairs. So that's carbon with the double bond. If we look at acetylene, which is C2H2, we would notice that the bonding here would actually end up being a triple bond between the 2 carbons and a single bond between the 2 hydrogens, or between the hydrogen and the carbon. Now you say, how did you come up with that so quickly? Well, you know that carbon's got to have 4 bonds, and you know hydrogen can only have 1 bond, and the total number of valence electrons here is 2 times 4 for the carbon, plus the 2 times 1 for the hydrogen. So that's a total of 10 valence electrons. And so 2, 4, 6, 8, 10, there's my 10 electrons in acetylene, and everything's satisfied according to the octet rule for the carbons, and then some people call that the duet rule between the hydrogen and carbon, that hydrogen can only have 2 electrons. So carbon, really important element because it can have multiple bonds. There's not a lot of elements that can have multiple bonds. So carbon has the ability to create an unlimited number of compounds when linked to each other, and that forms the basis of the field of chemistry called organic chemistry. All right, so this drawing of Lewis structures, this is something you should have had in your introductory general chemistry class. If you don't remember how to do Lewis structures, I encourage you to go back to that chapter in the Denniston book. I believe it's chapter 4, and refresh your memory about Lewis structures. Because what we're going to be doing with these Lewis structures, if you'll remember, when we did Lewis structures before, we took these Lewis structures and we were able to determine molecular geometries. And the way we did that was, if A represents the central atom, in this case carbon, and X represents the number of bonding pairs coming off of the central atom, in this case there are 4 bonding pairs, so we have a classification of AX4. That gives us an indication of what the molecular geometry of, in this case, methane looks like. So what happens here is the carbon is in the center. There's a hydrogen here. We use a solid line to represent in the same plane as the board. So we will have a hydrogen here and one coming out of the plane, which we'll use a triangle to represent that. And we'll put a hydrogen here, and then going back behind the plane of the board, we will have a hydrogen here. And you say, well, how did you come up with this shape? Well, again, when we do molecular geometry, these lone pairs want to be as far away from each other as possible, and in three-dimensional space, it is this geometry that keeps those bonding electrons between the carbon and hydrogen as far away from each other as possible. Remember, the angle here is 109.5 degrees, and that is the angle between each one of the hydrogen-carbon-hydrogen bonds, and that's much greater than if you drew this in two-dimensionally, then you'd have something like 90 degrees. So some people haven't had molecular geometry. They would think that yes, it would form some type of cross geometry, but again, this angle is only 90 degrees, whereas the tetrahedral geometry is 109.5. And just to refresh, remember why we call it tetrahedral. Hedral means sided, and there is one side of this molecule. Here's the other side. There's one behind and there's one below. And tetra means 4, so tetrahedral means 4-sided geometry. With carbon dioxide, we would classify this as AX2. Remember, when we're using the valence shell electron pair repulsion theory to determine molecular geometries from Lewis structures, and X2 again means bonding pairs coming off of the central atom, and in the valence shell electron pair repulsion theory, called VSEPR for short, that theory does not distinguish between a single, double, and triple bond. So even though there's actually 4 pairs of bonding electrons coming off carbon in the central atom of carbon dioxide, we treat each one of those double bonds as 1x. So that's why it's AX2. Anytime you see AX2, the geometry is always going to be linear, because you want to keep the bonding electrons as far away from each other as possible, and so by making this linear, you have 180 degrees as the angle. Same thing with acetylene. We would treat this a little differently because it does have 2 centers. It has a carbon here and a carbon here. But if we look at each one of those carbons, it's AX2, and AX2 is still going to give us a linear geometry. Why do we need to know this? Well, the next part that we need to understand when we're working with organic compounds is, once we know what the geometry is, which is very important, we also want to know, is the molecule itself polar or nonpolar? If you'll remember, polar molecules have positive and negative ends in the molecule themselves. They tend to dissolve in water because water is also a polar molecule, and the phrase is like dissolves like. So polar molecules will dissolve in polar molecules, and nonpolar molecules like oils, gases, maybe like this methane gas or gasoline, they do not dissolve in water because they tend to be mostly nonpolar. So that's why when we try to wash our hands and we have grease on them, the grease doesn't come off very well unless we either use hot water or we use a detergent, which creates micelles that allow the grease to dissolve in the micelle, and then the micelle to dissolve in the water. So how do we determine if a molecule is polar or nonpolar? Well, we have to have two parts. One is we have to know what the geometry is. The other is we have to know what the polarity of the bond is between the two elements. So if we look at carbon has an electronegativity, and that's what we'll be using to determine the polarity of the bond. You would look this up in a chart, but carbon has an electronegativity of 2.5, and hydrogen has an electronegativity of 2.1. Let's write that better, 2.1. So that's a difference of 0.4. Now, in some books they'll say this is a nonpolar bond, and in other books they'll say it's slightly polar. And so you'll have to make a determination there. I mean, technically it is slightly polar because there is a difference, but that difference in the scheme of whether it's a nonpolar, polar, polar bond, most people will say that this is a nonpolar bond. Again, it depends on what theory you're using. But does it really matter here? If we look at our geometry here, for methane, that means that there's a slight pull towards each one of these hydrogen's electrons to the carbon. And again, what this means is that over time, if we were looking at this over time averaging, because there's a slightly greater electronegativity on carbon than hydrogen, at any given time the electrons could be more around the carbon than the hydrogens. And over time we would see that because of the difference in electronegativity. But if you look at the arrows here all pointing towards the carbon, a lot of times we show that also by saying partially positive charges on the hydrogens, like so. We don't have a positive and negative end to the molecule. So knowing that, we know that methane as a molecule is nonpolar, which means it's not going to dissolve in water. So where does this become important in everyday life? Well, when we think of swamp gases, a lot of swamp gases are based on methane, and they're generated from decaying matter in the bottom of a swamp. And when that methane is generated, because it does not dissolve in water, it bubbles up and it escapes into the atmosphere. If it did dissolve in water, you would get a buildup of methane in the bottom of the lake or the swamp, and at times you would have a big turnover of methane, and you would have explosions in the swamp. So I don't think we want that. It's not to say that it can't, as the gases bubble up, that they can ignite. It's just that we wouldn't get a high concentration and a big turnover. Some people would argue, well, that could happen with if the swamp is cold, but again, most swamps are in warm areas. So we look at something like carbon dioxide. We'd also see that oxygen has an electronegativity of 3.5, and carbon is 2.5 for a difference of 1.0. So that's a more polar bond. The electrons are being pulled from the carbon over time to the oxygen because the oxygen is more electronegative. And so the oxygens have a partially negative charge and the carbon have a partially positive charge. But again, because this is linear, these two forces are pulling equal and opposite, and they cancel each other out, so carbon dioxide is also non-polar. I think about, when I think of carbon dioxide, I think of it as one of the things that it's used for is supercritical fluid extraction, and it has been used in dry cleaning, or it is used in dry cleaning. It's a way, most greases and dirts on your clothing, or most dirt on your clothing is greases and dirts which are non-polar, and they use carbon dioxide as a way to extract or to clean your clothes without using water. Acetylene, same thing here. We would have the carbons being slightly more electronegative than the hydrogens, but again, overall, the molecule would be non-polar. So maybe you're thinking, well, when do we get a polar molecule in organic chemistry? Let's see if we can move to the next slide. So what happens when we substitute one of the hydrogens in methane and we make it a fluorine? So we're going to have the precursor, methane, knock off a hydrogen and put a fluorine in it. So we still get the same geometry. We get AX4, and if we did the Lewis structure to complete this, it would look like this. When we draw the three-dimensional geometry, I'm going to put the fluorine up here. I'm just going to rotate it just to make it a little easier to see what's going on. And we'll have my three hydrogens down here. Again, the difference, electronegativity of fluorine is 4.0 and carbon is 2.5 for a difference of 1.5. So this is even a more polar bond than the bond between carbon and oxygen. So the electrons over time, average, would spend more time around the fluorine than the carbon. And then again, carbon being slightly more electronegative than hydrogen, the electrons are spending around more time around carbon than the hydrogen. So overall, these arrows are all pointing in an upward direction, like so. And so when we see an overall resultant vector force moving in a particular direction, that molecule is polar. One other way we can do this is always an easier way than to draw these vectors. If you can draw an imaginary line through the molecule so that one side is strictly negative and the other side is strictly positive or partially positive, and then strictly partially negative on the other side, you have a polar molecule, because that's what polar molecule means, that it has a positive and negative end to it. So this substance, because it's polar, it would dissolve in water. All right. Let's talk about the types of formulas that we're going to be using in this class. One is the molecular formula, and that's what you're used to seeing. This would be CH3. So we would call this methyl fluoride, CH3F. That's the molecular formula. This is the Lewis dot formula, but if I just showed it as these lines, we would call that a structural formula. It kind of gives us an idea of what the placement of the elements around the central atom are. Condensed formulas, this would also be condensed, but generally where we use condensed is something like, let's say I have 6 carbons, and we know that each one of these carbons has to have a total of 4 valence electrons around it. So at at the end of each one of these lines is a hydrogen. This is called a saturated hydrocarbon because it's all single bonds, and wherever a carbon is not bonded to another carbon, we have a hydrogen bonded to it. So this is called because it's single bonds, it's a saturated carbon. It's also called a hydrocarbon because it's a hydrogen carbon compound. And so what I've drawn here is a structural formula for hexane. How did I get hexane? Well, I look at the carbons. I've got 1, 2, 3, 4, 5, 6 carbons. And 6 carbons, we use hex to represent that. And since this is a saturated alkane, alkanes are just carbon hydrogen based single bond based compounds. This is called hexane. So instead of drawing this big formula that takes up a lot of space, I could write CH3, a methyl group, and then I could put in parentheses CH2. Oops, did that incorrect. All right. CH2. Then close the parenthesis, and I've got 1, 2, 3, 4 of those units. So I'd put a subscript 4 outside the parentheses, and then I would put another methyl group on the end like so. That's called a condensed formula. Condensed formula. Much easier to write, doesn't take up as much space. Another formula that is very popular is, instead of the condensed formula, let's make it even easier. To represent these 6 carbons, which are, if you'll notice again, if we look at each one of these carbons, they would be in AX4 classification. They would be tetrahedral in shape. So this carbon sometimes is written like so, where every point represents a carbon. So we'd have a carbon here. There's 1, 2, 3, 4, 5, 6. So this is called a line formula, and like I said, it's very popular, easy to draw, doesn't take up much space. And what's assumed here is that at each one of those points, we know the carbon has to have 4 bonds. So this carbon at this point here, it has a bond to 2 carbons, so that's 2 bonds, and we're not drawing in the hydrogens. So there would be a hydrogen here and a hydrogen here, and then on the end here, because you only have 1 bond, there would be 3 hydrogens. Oops, let's go back. 3 hydrogens attached to that end carbon. So in a line formula, much more simple, and takes up less space, and we're going to be using the line formula quite a bit in this course. Alright, classification. The first group of organic compounds that we're going to talk about is the alkanes. The alkanes have a formula of CnH2n plus 2. So if I have C4, then I must have H10. So what does that look like? Well, again, we could do it as a line formula, and it would look like that. This would be carbon 1, 2, 3, 4. And we know that off of this carbon there are 3 hydrogens. Off of this carbon there are 2 hydrogens, and 2 hydrogens off this carbon, and 3 hydrogens off this carbon. So if you add those up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Line formulas are the way to go, unless you need more information. So much